This is a picture of found on page 565 of Unit 23 on compressors, and this basically shows a figure, 23.47 scroll compressors drivetrain showing the center bearing and the motor shaft offset. Here we have, I believe this is a Copeland, this would be a discus compressor. This illustration is found on page 562 under Unit 23. And this basically shows the semi-hermetic arrangement of this compressor. Notice on this end here, this is not a splash feed lubrication system, but an oil pump. We have an electronic, what they call a centronic oil failure switch, and this is electronic in nature. There's a red button basically to reset in the event we have a loss of oil pressure. But I will caution you, before you reset this loss of oil pressure in this compressor, it's really important to take a look at this sight glass to make sure that we have sufficient oil inside there. Otherwise, damage can and will occur. Here we have a York centrifugal. Notice that we have the cooler section and the condenser section separate. You will find these in hospitals, large office buildings, industrial sites. The panel that operates this centrifugal typically is going to be electronic in nature. It basically has a very easy to follow menu telling you all the pressure, temperatures, things that's going on inside this system. And notice in this particular case, the motor is external here. This could be a hermetic design, possibly, if you look at, and I don't have a very good picture of this, but looking at this, you would, the motor is separable in this case. So motor can be repaired. So I'm going to assume that this is not a hermetic design based on this particular picture here. Okay, here we got a reciprocating compressor. You'll see lots and lots and lots of these out there, not on new equipment necessarily, but on a lot of the equipment that's been around 15, 20, 30, even 40 years. Typically, you will have your start common wiring harness. It'll usually be of a plug design now instead of separate wires like in the old days. And basically your motor terminal connections are right here. These wires that are wrapped around the case of this hermetic compressor are your oil heater. This heater is energized during the off cycle to prevent the oil from leaving this compressor. The idea is if we heat the oil, the refrigerant and oil will separate, and there'll be sufficient oil left here to start and lubricate this compressor upon demand. And of course, you have your piping connections. This is probably going to be your low side connection here. This will probably be your high side connection, and this would be like a service port. Here we have another version of what appears to be a discus compressor, but I am going to follow up on this. In fact, this is on page 563 of your textbook, figure 23.44. This is an intelligent stored discus compressor with integrated system electronics, onboard diagnostics. So this is pretty much state of the art. Once again, we utilize a force feed oil lubrication system. We have a Slentronic type protection for the oil lubrication system. And of course, the good old sight glass. This is still considered a semi-hermetic because this compressor can be rebuilt. The heads can be, you can actually do a valve plate change in the event that the valve plates go bad. You can also overhaul this compressor. So basically, this compressor has the ability to be rebuilt like a motor on a car. Now this appears to be like a spline shaft type connection, and I want to get some interpretation of this because I've seen this a lot. Interestingly enough, if you have a vacuum pump, they utilize this type of a connection in order to for the motor to operate the vacuum pump. As an example, a JV vacuum pump. I actually have vacuum pumps that utilize this drive type design. Notice that you have like a rubber type spider here, and then you notice you have these forks. So basically, one side comes from the motor, the other side comes from the compressor. These integrate. These are very forgiving as far as alignment goes. But that being said, what usually happens when you have a problem with this this spline drive line, what is usually the weak link right here is going to be this rubber disc right here. This thing will snap and break, and when that happens, basically the compressor, or in this case the pump, which I have in the way of a vacuum pump, is not going to operate at all. This is a very common drivetrain type. I don't actually see this illustrated in your textbook at this point. I am still attempting to find it. There it is. I found it on page 560 of your textbook. It's under figure 23.38, a flexible coupling. And it says here, an extensive procedure is used to obtain the correct shaft alignment. This must be done or the bearings and the seal will prematurely fail. Like I said, the alignment is not as critical. It's still critical, but not as critical. But this is a fail-safe design, and I've seen these on our vacuum pumps that we have in the lab, as well as the ones I personally own. Okay, this is old school here. This is an old reciprocating compressor. I ran into these a lot when I was in the US Navy on active duty. These compressors were made by Carrier Corporation, and basically this is a belt drive design. And this, of course, was your piston slapper, as I refer to it. Notice that you had the motor over here. Of course, the shaft is parallel on the compressor to the shaft on the motor. The belt tension had to be very, very good. You wouldn't tolerate misalignment. In this case here, we had I believe this was the liquid receiver for this particular reciprocating type unit. And by the way, this is found on a page 560. They call this a multiple belt compressor Tecumseh. This is old school. You will not see this in new buildings or new construction at all anymore. And one of the problems with this belt drive unit is the shaft seal, because that's where leaks occur, and it does happen all the time. Okay, here we have a scroll compressor by Copeland Corporation. You have the orbiting scroll as well as the fixed scroll. An excellent design. They can tolerate some liquid, whereas the reciprocating piston slapper, as I like to refer to it, cannot. So that being said, this is a good design. They hold up very well. And this is the 5th generation scroll compressor. You can find this on page 564 of your text. There's a picture of the fixed scroll and the orbiting scroll, and of course the discharge coming up through the top. Okay, here we have a little bit of a interesting compressor arrangement. I want to verify what type this is before I tell you what it is, because if you'll notice that the motor is external, so this tells me this is a serviceable type of compression unit, so that in the event that we have a motor problem, we can take this thing and remove the motor and repair it. And notice that they have sight glasses down here, and you have your filter dryers, and these are your 4-inch Henry cores that can be replaced. on a periodic basis in the event that we detect moisture in the system. And let's see if I can find that picture. This is made by Frick. I believe that's a division of York International, if I remember correctly. They make low temperature type equipment. Okay, this is a screw compressor made by Frick. So basically, this is different technology. This is for large capacity air conditioning or refrigeration systems. Okay, I've worked on a bunch of these. This is a train. This would be a direct drive reciprocating compressor. You'll have your sight glass for your oil lubrication. Right here, you have a shield to protect the operator when this motor is operating. So this motor is directly coupled to this compressor through the use of special hubs and a flexible coupling here. The alignment of this shaft and this motor is critical, and it can take days to get within 2 or 3 thousandths of an inch angular alignment or the other types. In other words, you have to use a dial indicator. This is a slow, tedious process. If you take a motor out, you can figure on at least 8 to 16 hours to do the alignment on these things. There is no speed up mechanism. And the other problem is because there's the shaft, it goes outside of the compressor housing, requires a shaft seal. And over time, the shaft seal will wear and leak. Here we have a Copeland compressor. This would be a standard reciprocating compressor. These have been around for years and years and years. This particular one is a splash feed design. It's got the oil sight glass here. We don't have an oil pump. And then here is the valve plate where I have my mouse here. This is where the valve plate's located. When the valve plate goes bad, basically you have to get a new one with the gasket kit. And then of course you have to remove this head, remove the refrigerant, obviously. You have your service valves on both sides, your electrical connections over here. I've seen a lot of these compressors from my naval days, as well as working for Amtrak on passenger cars. I see these a lot on there. They use a carrier version, which is the 06D, 06E semi-hermetic compressor design, which this is. If you have to add oil, your oil fill port would be right here. Very simple, very easy to work on. They do a great job as long as your refrigeration conditions are correct. Okay, this is inside that Copeland hermetic, semi-hermetic compressor. In this particular case, we have an oil pump in here. Here we have 3 cylinders on this one. Interesting. So you got 3 cylinders here, your crankshaft here, and then of course your suction gas. The motors on these semi-hermetics are always cooled by refrigerant. If you don't have refrigerant, you have no cooling. The compressor is going to overheat and the thermal overload will shut this thing down. So no refrigerant, no cooling, and you are going to have issues. These compressors are field serviceable and rebuildable. Now, this is an example of your alignment. This is illustrated in your textbook, but I want to just show you what goes on here. Now, and if you have a belt drive unit, if you have angular misalignment, very serious situation here. So you are going to employ the use of a straight edge in order to get the alignment correct. Okay, here's an example of parallel misalignment. This is correct alignment. The straight edge is going to get you there, but in some cases you may have to use a dial indicator on a magnetic base to verify that there is no misalignment, or there could be a problem with the pulley or something like that. So just using your eyesight in order to determine correct alignment is not good enough. You need a straight edge, and basically you have to check this out. Now notice on this angular misalignment for the multi-belt, this is a very severe case. I've never seen it this bad. I have seen it this bad. Once again, the straight edge is absolutely critical in order to get those belts to go in a correct position. One thing I want to call your attention to, notice that the groove of the motor pulley versus the compressor pulley is different. What we are aiming for right here, look at this center line. This center line has to be perfect. So we're going to take the center groove of this 3-groove pulley and make that our fixed point in order to assure perfect alignment as far as the belt drive is concerned. Okay, one stage of compression as refrigerant moves through a screw compressor. So this would be an example of how a screw compressor works. They utilize these screws that are what we call a lobe type thing. They work very well. You can find this on page 550 of your book under figure 23.18. They're tapered machine screw type gears. These are precision type castings, and which are carefully machined. Alignment, of course, is absolutely critical. Notice that you don't have a valve plate per se. Basically, you're going to move a large amount of refrigerant vapor through these screws in order to create the compression process. You'll find these on large capacity screw chillers. Once again, we have the semi-hermetic compressor. Notice that we have the oil pump end over here. This particular one is just an illustration from Train. Now, the one thing I want to show you, notice that you have drilled passageways inside this crankshaft. Basically, this pump is going to force oil through all these openings right here. And those openings are critical for the operation of this compressor. So that oil is going to travel from here all the way down here to the end through these drilled passageways. So as any place there's a bearing surface, they will get oil, they will get lubricated, okay? Here we have another example of a hermetic compressor. Notice that the compressor, the pistons are horizontal. Your motor here is on top. The only thing I can tell you about these, they either work or they don't. Basically, if you have an electrical failure, this whole thing has to be replaced as a complete assembly. There is no work that you can do inside. One of the things we used to do years ago, just in class, we would actually take these compressors that were condemned out in the field, and we would cut this weld feed and take them apart to determine what caused these compressors to fail. I can tell you just from years of experience working on hermetic compressors, number one problem was lack of refrigerant, big time. Lack of refrigerant. These units do not operate very well for very long if you have a shortage of refrigerant vapor, or if you have liquid slugs coming in here. You'll destroy the compressor mechanical. And one of the things that you need to determine when you're replacing compressor, you have to ask 2 questions. Was it electrical in nature or was it mechanical? And based on what you find out, then you can determine what the process of replacing that compressor is. You just don't take an old compressor out, stick a new one in without determining the cause of the failure. Okay, hot gas muffler. This is mounted in a horizontal installation. Don't forget, a muffler is designed to quiet these compressors' pulsation noise. They're not designed to eliminate vibration. They are designed for noise and noise alone. Okay, here we have what appears to be a 3-phase compressor. Reason why I say that, because you have T1, T2, and T3. Now, so you have 3 sets of windings. You also have a 3-phase internal thermal motor protector. If you lose one of those phases, if for whatever reason, one of those 3 sources of power drops out due to an electrical whatever, basically the other ones are going to see an increase in current as this motor continues to try to turn, and it will heat up and it will shut down, okay? And when that thing shuts down, it's going to basically open up all 3 of those normally closed switches in the center of this diagram. Now, if you're called out to the job site and you are going to troubleshoot this motor, you need to determine what caused the overload to open. Just because the overload is open doesn't mean the compressor is bad. The one thing you need to get in the habit of, if you're not, is to take your hand, the back side, not the palm side, the back side, and feel the compressor dome. If it's super hot, the first thing you need to do is cool that thing externally with ice bags or water. Bring the temperature down. Once you bring the temperature down, the internal thermal motor protector should reset, should restore your resistance readings, and then you need to determine the cause. And I would bet you most of the time you have basically a shortage of refrigerant, cool vapor, keeping this motor cool. Here we have a Copeland scroll compressor, has an internal pressure relief valve here, suction connection right here, discharge connection. Now, this internal pressure relief valve on the later model scroll compressors, I can tell you this thing is going to open up if you're trying to use this compressor to take and pump down the refrigerant inside a condensing unit. If you drop below a certain point, that internal pressure relief valve is going to open, and it will not allow the scrolls to continue to pump refrigerant vapor. Be aware of this. You won't find this so much on the early compressors. The ones that are in current production, absolutely. This is designed to prevent these compressors from destroying themselves. They're not really designed to go down to 0 PSIG unless it's a low temp model compressor. And I'm not talking about air conditioning right now. Okay, here we have the fixed scroll. This is the discharge port. Okay, here we have a check valve, which, let's see. In a check valve, I want to see what the book has to say about this. I'm kind of curious. Okay, this will be found on page 566 at the top. This would be 23.49. So it says here, the top side of a non-orbiting or fixed scroll showing the discharge valve. So basically on B, that is going to be your discharge valve. Okay, we talked about this earlier, the compression cycle on a reciprocating. And remember, compressors are designed to pump low pressure, low temperature vapor, not liquid. This is part of that reciprocating cycle, which we talked about in the previous slide set. This shows the bottom dead center. Shows the piston starting up. Still a small amount of refrigerant at the top of the stroke. And here, of course, this is the scroll compression cycle. Gas enters the outer opening as one scroll orbits the other one. You got a fixed and an orbiting scroll. Then the open passage is sealed as the gas is drawn to the compression chamber. As one scroll continues to orbit, the gas is compressed into an increasingly small pocket. The gas is continually compressed into the center of the scrolls, where it's discharged through precisely machined ports and returned to the system. During the actual operation, all passages are in various stages of compression at all times, resulting in a near continuous intake and discharge. Okay, this particular compressor has the ability to operate at two different levels, 100%. The bypass ports in this particular case are closed. And if you're going to only operate at 67%, I'm going to assume that the motor is a two-speed design, not variable. Then basically what's going to happen is the bypass ports open. So what they're doing, they have ports that are controlled based on the capacity requirement of the scroll compressor. Okay, here we have a picture of a digital scroll compressor. Now, we do have a scroll unit down below. I'd like to, okay, and this is found on page 569, and this is going to be figure 23.54. It's an internal view of the head, the digital compressor, digital scroll compressor showing modulation chamber, bleed hole, lift pistons, and solenoid valve. So basically, by opening and closing those bypass ports, we can change the pumping capacity on this, not necessarily the speed. Basically, we just open and close those ports through this piping arrangement and solenoid valve. Okay, this is basically a cross section of the scroll compressor, and this is what it looks like internally. This is found on page 571, and it has a variety of internal safety controls for this thing. They got a temperature operating disc, internal relief valve over there at number 2. We talked about that. A floating seal, which is number 3 over here, and the motor protection, which is number 4, located right here. So we have a lot of safety things. These compressors offer very long service. They work extremely well. They're very reliable. Scroll compressors, I can tell you I've changed a few over the years, but they're few and far between. I would say in usually a cooling season, maybe I'll change 1 or 2 of these a year, and that's about it. As long, and on my maintenance accounts, they usually last over upwards of 20 years plus, because I check the refrigerant charge, I check the run capacitors, I do all the maintenance, check everything out, and these things are designed to run, well, I won't say forever, but they do run a long time. Okay, here we have the variable pulleys for your belt drive, like for your blower, for your compressor. So the flange has the ability to move in and out depending on the belt size. The one thing I got to call your attention to is when you adjust these things, you're going to change the speed of the compressor RPM, which is not a bad thing depending on the application, or the speed of the motor operating a blower fan. It's very important that you take and amp out the motor. Make sure you do not exceed the load factor on the motor once you change the opening of this. And the other thing which we talked about previously, we need a good alignment. We need the alignment has to be right on a parallel shaft arrangement in order to prevent premature failure of the shaft seal. Okay, here we have a, this looks like a turbo core compressor. I'll verify this in just a minute. I have seen these, yes. This is a turbo core. This is an oil-free centrifugal compressor with variable frequency drive, and has onboard digital controls with the magnetic levated bearings. In other words, no oil. Do these things work? Sure they do. Are they expensive? Sure they are. But they have a whole bunch of safety features. I've seen one of these over at Kaiser Permanente Riverside campus. They installed one a few years back. They had some issues with it. I don't know if they ever solved them. But as you can see, this compressor operates at a very high speed, and all the parts, basically you're just going to check electrical, you're going to check the pumping capacity. But look how small those centrifugal scrolls are. Very interesting, very, very small. And this appears to be a 2-stage design based on what I see here. Okay, here we have a wiring diagram. Notice that we have an internal loader coil, a run capacitor, L1, L2, molded plug with rectifier. Now, what is this wiring for? We'll just tell you here in 1 minute. Bear with me. kind of curious what that wiring diagram represents inside a compressor. Want to make sure. Okay, I think I found it. That's found on page 568 at the bottom under item C. This would be figure 23-52. Basically, what happens here? Okay, let's see. Okay, this is the electrical diagram of the internal unloading and compressor motor circuit on the scroll compressor. Notice that they use a solid state device here because we have a rectifier installed. So here we have scroll compressors. You're going to see this, the fixed and the orbiting scroll. This is also on figure 2352. And basically, this is the internal loading mechanism showing the modulating ring and the solenoid coil assembly. Here we have a picture of the scroll. Okay, very easy device to understand. What I love about scroll compressors, they're very simplistic. Okay, and this is going to be figure 23.50 on page 566. The scroll member is showing the tip seal for axial loading. Here's another picture of the scroll compressor. Notice the simplistic design. These things, like I said, they run forever. I've never had any issues to speak of with this particular compressor. They just are of a very good design, and depending on the model and stuff, they will give you many years of good service as long as you can maintain the proper refrigerant charge. That's going to be number one, most critical. If the refrigerant charge is not maintained, if you have a leak, you're going to have problems. These compressors must have a decent amount of refrigerant going through this, okay? And I'm talking about refrigerant vapor, by the way, not liquid. Here's your fuse tight connection. Transfers electrical energy from the fusible, from the wiring outside of the compressor into the motor windings inside. I have seen these things short out. I have seen these pins blow out. Be careful. If you have an acidic condition, I've actually seen the fuse tight get attacked. And over time, these things actually, if you just happen to go work on these wires, and let's say you pull the molded plug assembly off of the individual wires, I've actually seen these terminals blow out and lose all the refrigerant charge, and certainly could cause injury if in the wrong spot. So I'm going to urge caution when you work on these fuse tight connections, because in some cases they have been known to be compromised due to weakened conditions inside the compressor. Okay, here we have a discus valve. Notice that we have a conventional valve design here up on top. This would be a reed valve, intake, discharge. Now we have a little bit different situation. Still have an intake valve, but with the discus valve is your discharge out. So basically now we put just a valve plate here on this side, and then we allow this disc to move up and down in order to discharge the refrigerant gas which has been pumped. Okay, here we have a valve plate, and these fingers prevent the reed valves from extending too far. This is your gasket assembly. When you take these things apart, you're also going to have to take the gaskets out and put in new gaskets. The gaskets have to be oiled, the heads have to be torqued down, and you have to use what they call a torque chart. You just don't go around the perimeter and tighten the bolts. You have to tighten in a certain manner in order to put in a uniform pressure on this particular head assembly. I've done this over the years. It's not rocket science. It does involve the use of a click torque wrench, and you have to know which bolts. The manufacturer will give you a chart showing what bolts in what order should be torqued down when these things are replaced. So this is a field replaceable valve plate on a reciprocating compressor, probably a semi-hermetic. Okay, here we have a wiring box here. I saw this here just a few minutes ago. Notice how the wires are hooked up inside of this particular mechanism. And this is a three-phase design. You're going to find this illustration on 588, and this will be figure 23.34. Notice that you have 24 volts over here to S1, S, and then you have line voltage, L1, L2, L3. And then if you have a two-speed, you're going to have your second, you're going to have one speed here, another speed here. Notice this is the wiring going to the contactor. And then you got the contactor coil. And then of course you have your motor electronic protection module. The idea behind this protection module is simply this. If we detect an overload on either L1, L2, or L3, we're going to shut this compressor down. Compressors have to operate at a very balanced voltage. We're not allowed, if I remember correctly, more than 2%, but phase to phase. In other words, T1, T2, T3, the voltage can't really vary more than 2%. So if it's not done correct, if the voltage isn't correct, you're going to have a problem with current draw. You're going to have a lot of issues. And that's what this module is designed to do, protect the motor or the compressor. You have semi-hermetic compressor again, showing the oil pump here at the bottom, your piston rod, upper bearing, crankshaft. Typically, you're not going to tear these things apart. This is what they look like internally. They've been around for years and years and years. But on new technology, air conditioning, you will not see too much in the way of reciprocating compressors no more, because they're not as efficient as the scroll compressor. Okay, here we have parts. Notice that they have the spring, the seat, the valve ring, the valve cage. Now the question is, what is it? It's a valve plate of some kind. Valve plate of some kind, and the question is, what kind? Saw it here earlier, so bear with me. For some reason, I'm having a little bit of trouble trying to find this illustration. Please bear with me. You know it's in here, because I did remember glancing at it briefly. Unfortunately, glancing, and oh, here we go. This is on page 553 under figure 23.26. This is your ring valves, basically on this compressor. Okay. So basically it's a small set of springs. Basically this is on a train compressor. So there's many different types of valve plates, valve assemblies. Just make sure you understand how they work, and typically these parts are field replaceable. Okay. You can order parts from the distributor and rebuild these compressors if it's of a semi-hermetic design. Okay, here we have the, this shows the train compressor utilizing that particular valve spring mechanism. Notice that you got the gas accumulating on the top, you got the disc in the center, and you got the springs on the left and the right side. So the suction valve is on the towards your right. And this, by the way, is going to be, hold on a second. I believe that's the, I believe this is going to be found on page 553, and this will be under figure 23.27. Here we have the internal spring mounts. Now, what has happened on these hermetic compressors? If you have liquid refrigerant hitting, I've actually seen those internal valve springs break. And when they break, here's what happens. The motor is no longer equally supported on 3 or 4 springs. And what has a tendency to happen is the motor tends to lean towards the shell. And in some cases, the motor winding can get damaged and eventually cause a ground, which will shut down the compressor. And obviously, you're gonna have to do something about it. Okay, you have the suction line, discharge line, and of course you have the external springs to eliminate vibration. Now this is called comfort alert. This is a kind of an interesting thing here. What happens is, let's say that you either have a 3-phase or a single-phase motor. The wiring from the compressor is going to be passed through these open holes, one for the run winding, one for the common, and one for the start. And what happens is you have an LED that's going to flash off a code. This is the diagnostic key showing what's happened. So with this comfort alert system, basically it's going to show what happens, and it's going to give you the indication through the flashing, and it'll show you if it's in a trip position or an alert position. So if it's an alert position, it's going to indicate the fault code. Red position indicates the compressor has tripped or has no power. So in some cases, the compressor will lock out, some cases they won't. I've actually seen these on residential units. The comfort alert system works. It works very well, and it's an additional form of protection to prevent that compressor from damage. Here we have magnetic bearings levitate the motor shaft, and this will be on a turbo core compressor. Notice that you have those centrifugal wheels over here. Notice there's no oil lubrication taking place here. This particular unit is basically going to, what's going to happen here is this thing is perfectly balanced and in a magnetic state so that this motor can turn at a very high rate of speed. Remember, on a turbo core magnetic bearing compressor, you don't have oil. Use the magnets to do the same thing. It's kind of hard to figure out sometimes, but I will tell you that it does work. Okay, now we have a situation over here on a semi-hermetic compressor. Look at those reed valves there. They are not very good. We have a situation there where damage has occurred. You'll find this on page 23.28. And this would be item D, the valve plate with broken discharge reed valves. I can't tell you how many times I've seen this, but the cause of this is usually liquid. And what is interesting is where the parts are. If this is broken, where's that metal at? Because this thing goes all the way here, sits here, and basically, if this is broken, that means the metal is somewhere in the system. Hopefully, it's in the crankcase of the compressor, or it could be in the refrigerant lines going to the evaporator. It could be anywhere. It's hard to say. I always ask the question when I tear one of these things down, where are the rest of the parts? If all the parts are not there, that means the metal has traveled through and basically chewed something else up in the process. Okay, here we have another valve plate assembly right here. Notice that they have O-rings here. These are O-rings, which is kind of interesting. And I might add, these are high temperature O-rings, okay? They are designed to take literally a lot of heat because, as we know, compressors compress refrigerant gas. And as you compress refrigerant gas, over time, that gas has a tendency to heat up the surrounding area. And those those O-rings in this case, instead of gasketing material, can break, they can harden, they can solidify. I'm going to guess, based on what I see there, that looks like a Train product. I haven't seen those for a while. I remember the early train hermetic, semi-hermetic compressors had O-rings very similar to this. So based on what I see here, this appears, and I'm just going to say it appears to look like a train design as far as the valve plate is concerned. And the thing you got to pay attention to is those O-rings. Over a period of time, those O-rings will get hard, they will break, they will leak, and they have to be replaced. Okay, so basically, this is okay. This is on page 563, figure 23.43. This is your discus valve plate. So this is actually a Copeland product. Okay, so this is a Copeland. This is a discus valve. And these appear to be the high temperature O-rings. So this is not necessarily a train product. I have seen something similar to this in train equipment. Okay, here's your valve plate assembly. Notice that you have your pins, and notice how this you have this O-shaped ring design here. You're going to find this on page 562, item D. And this would be under figure 23.43. This is your discus suction valves right here. Very similar to the standard reciprocating. I've seen these. They're made of spring steel. I've actually seen these things snap and break. Beware of that. Okay, here on, this is item F under figure 23.43. This is a discus valve plate showing the discus valve. This is on page 563. Okay, here we have these, what I call the finger valve plates on a reciprocating compressor. I've seen these things a lot. I have seen these things get destroyed because of liquid slugs. Be aware, this is how they're supposed to look in the perfect environment. Notice that the gasket's been removed. Notice that this thing sits on these pins. Notice that these sit in this recessed part of the cylinder. So this is what the valve plate should look like as far as these valves are concerned. Hopefully, if you have a compressor pumping problem, you're going to find out where those parts are. And one of the things I haven't said yet, I'm going to tell you right now. By the way, this is on page 554, figure 23.28. And this item here basically is your suction reed valves. If you have a compressor that fails, when you take the compressors out, typically you're going to trade these things in as a core. There's nothing in the trading in of cores to prevent you from taking these compressors apart and finding out what damaged them. I would encourage that, because if you open these compressors up, you can see what actually happened. And yes, it takes a little bit of time, but by the same token, you need to ask the question, why did this compressor fail? It's not because of old age, by the way. Compressors fail for electrical or mechanical reasons. And this is the reason why you want to do an inspection to verify this thing either works or it doesn't. Okay, here we have an eccentric type of crankshaft here. Now note, when I say eccentric, instead of having, what we have is, instead of having the offsets here on the crankshaft, we still have them, but basically we have a large disc here, and it is designed to stroke up and down based on this large design disc, which is going to rotate this piston motion. Okay, here we have a crank type crankshaft with a your pistons, very similar to automotive technology. Your wrist pin, your connecting rod, your piston. Of course, you have your piston rings. Nothing magical about this. For you guys that are automotive inclined, this should not be a mystery to you whatsoever. Okay, here's a valve plate taken apart. This is what shows like when you take apart a semi-hermetic compressor. And this is going to be found on page 553 under figure 23.27. This is your reed or flapper valves. held down on one end. This provides enough spring action to close the valve when burst flow happens. So once again, if you have an issue with it, you take it apart, find out what's going on with your valve plate because you don't have the ability to pump. You need to examine these valve plates to see what's going on. See if they're broken. Let's see if you have liquid slugs that cause damage to the plate. Chances are that has happened. This illustration, which is also on 552, towards the bottom on the left side, the piston rings for a refrigeration compressor resemble the rings used in automotive pistons. Very similar. So you got two rings in this case. Do rings wear out? Sure, absolutely. I will tell you, as a service technician, you normally will not rebuild these in the field. You will turn in the compressor and buy a rebuilt, remanufactured exchange. Very, very seldom do you take a compressor apart and replace parts, with the exception of the valve plate. Okay, here we have a cross section showing the how the electrical studs are mounted in order to hook up power. I've actually had these things on Copeland compressors blow out because they were not installed correctly in the rebuilding, remanufacturing process. I have seen refrigerant leak out of these things. You got to be very careful when you tighten the lug, the wire lug, or the wire to this bolt here, because if you over tighten it, you risk taking and breaking this seal here, and you have a situation where you could actually cause an electrical short or refrigerant to blow out through the terminal. Part of this is due to when these things are rebuilt, they are rebuilt by a subpar remanufacturing organization. And this we found on page 556 under figure 23.33. These are motor terminals. The power to operate the compressor is carried through the compressor shell, but must be insulated from the shell. And it's a fiber block used as an insulator. O-rings to keep the refrigerant in. Okay, this is a shaft seal design on a compressor that has an external, either a direct coupling or a parallel, have as a parallel pulley to operate this compressor. These shaft seals, they have a rotating element, which is a carbon type design, and you have a seat, which could either be ceramic or stainless or something of that design. And it's very important that these seals are making direct contact across 360 degrees of that fixed element. If you have dirty oil, if you have problems with parts, copper shavings or things circulating in the refrigerant and the oil, I've actually seen these shaft seals score. These shaft seals can and do wear out, and they have to be replaced. And it's very important as a refrigeration service technician, you get your leak detector out there if you're working on a shaft seal design to see if it's actually leaking or not. Sometimes you get lucky, they're not leaking. Sometimes they do, and you have to just deal with it. Okay, this appears to be a rotary compressor design. When we say rotary, we'll talk about that in just one second. You'll find rotary compressors typically on window air conditioners. You'll also find them on mini splits, very popular. The speed can be ramped up, ramped down. They work extremely well. They're very efficient. But once again, when these compressors go bad, you basically replace them. There's nothing you can do with them to fix them. You want to correct the symptoms, of course. But other than that, there's really nothing else to fix on these things. And this is found on page 545, figure 23.7. Here we have a bimetal overload. And basically what's happening here, this is embedded in the windings. The idea being is if that winding overheats for any reason, shape, or form, that overload, which you cannot directly access, which is internal to the compressor, is going to open up. This is going to be found on page 556, figure 23.34. internal compressor overload protection device that breaks the line circuit. Because this is a set of electrical contacts inside the refrigerant atmosphere, they're enclosed inside a hermetic compressor. If the electrical arc was allowed inside the refrigerant atmosphere, the refrigerant would deteriorate in the vicinity of the arc. Okay, so what are we saying in all this stuff that I'm trying to read to you? Basically, what I'm telling you is this. If that winding overheats, that bimetal is going to open up. You'll know this because you will not get a resistance reading either on the common start run if it's single phase, or the T1, T2, or T3. If that thing opens up, you get no resistance reading. That does not mean you have a bad compressor. It typically means the compressor is hot, lack of refrigerant, and basically use the backside of your hand to feel the temperature of that motor shell. If it's very hot, cool it down with water or ice. Once you cool it down, that overload protection device should reset internally, and then you can find out what caused it to trip. And most of the time, it's going to be a lack of refrigerant. Okay, here you have the a dipper. Interesting. This is a reciprocating compressor with a dipper assembly. Now, what do they mean by a dipper? Is this a splash type oil lubrication system? Let's find out. Because on the splash lubrication system, you would typically have like little sticks that would actually throw oil into the cylinder walls. But I don't see that in this example here. Hold on while I'm trying to find the identification for this. Doesn't appear to be showing up. I'm kind of curious what those dippers are. They appear to be taking the place of a like a cup. Oh, here we go. This is on figure 23.22 on page 551. Splash lubrication system that splashes oil up into the parts. So this is one method of getting that oil into the critical parts of that crankshaft and the piston connecting rods, that kind of thing. Okay, here's a compression. We talked about this earlier under the PowerPoint. Notice that we have a first stage and a second stage compressor. We amplify the pressure of the first stage into the second stage in order to reach a higher discharge pressure. So we're going to go from 100 to 169 by the use of the second compressor, where the piping of the discharge line goes into the suction line of the second compressor. Okay, low temperature 404A. 404A is a low temperature refrigerant used on refrigeration walk-in boxes, display cases, that kind of thing. I believe that's an HFC refrigerant. I don't recall. I'd have to look at the chart to verify that. But if you notice that this refrigerant is evaporating at -14 degrees, but it is superheated to approximately 50 degrees before entering the compressor. Why do we want to superheat the refrigerant? Because we don't remember, I've said earlier, and I'm going to say again, you'll probably get tired of me saying that, compressors are designed to do what? Pump liquid or vapor. They're always designed to pump vapor. Once you understand that, if you don't learn anything else from me today, this is extremely the most important thing I can leave with you. It's very important that you understand that this is a very critical point as far as reciprocating technology is concerned. So please don't forget that. I'm looking for this particular page. which I know I passed over. Okay, here we go. I found this on page 545 on page 545 under figure 23.4. A refrigerant entering the compressor is called heat laden because it contains the heat that was picked up in the evaporator coil from the boiling off process. The gas is cooled but full of heat that was absorbed from the low pressure of vapor and temperature of the evaporator. When this gas is compressed in the compressor, the heat concentrates in addition to the heat absorbed in the evaporator, and the act of compression also converts some of the energy to heat. Once again, reciprocating compressor, in this case it's refrigeration duty, we're using R404 alpha. I believe that's still used out in the field today. Okay, these are your valve plate assemblies that you would find like on a 5F, 5D compressor, 5-line series. Worked on these things. These are, or you could find a valve plate like this on an 06D or an 06E compressor. These valve plates are bulletproof. They work extremely well. Okay, the intake stroke. This is obviously, it looks like the discus, looks like a discus design. There's the springs we talked about earlier, and here's that discus valve that we talked about. And of course, you got your suction valves over here, and of course, your discharge valve is the discus. Compression stroke, basically the top end of the cylinder head. Okay, here we got the semi-hermetic again. In this case, this is probably going to be the discus compressor. And you got, this is an oil pump. You got your electronic oil failure switch right here. And of course, you got your oil sight glass here. A Copeland scroll compressor. Seen lots and lots of these. However, let me verify that is, that is a scroll compressor. Okay, so that's what it looks like when you get it. But what's interesting, notice that you got two terminals here. So this indicates that we have a 2-speed operation on this scroll compressor. So basically you got two wiring harnesses. And if I remember correctly, the wiring harnesses are not interchangeable between the first stage and the second stage. There's a reason for it, because they don't want you to put the hook these things up wrong and cause a burnout. So just be aware, if you have a molded plug assembly and you're trying to operate this thing and it's a 2-speed design, which this one appears to be, which I'll verify. Okay, so this is going to, this would be part of that 2-stage compression technology right here. Okay, so anyways, this has the solenoid. Basically, you have your electrical connections for the first and second. Basically, this compressor operates at 100% or 67%. Okay, we have the discus compressor again. This has forced lubrication because it has the oil pump and this electronic oil protection system. These things are bulletproof. They work very well. In this case, you don't have the ability, you have a push button, but it's located down here. Unfortunately, when these compressors lock up due to a lubrication problem, the inexperienced service tech, his first thought is, well, if I just reset that lubrication switch, all is solved. That's not the case. If this thing trips, that means we have a lubrication problem. And you will notice it in the sight glass. In this case, this one's blocked on this side, so I'm going to assume on the other side, the sight glass is available. You need to look at the sight glass, see if we have excessive refrigerant migration into the crankcase. And if that's the case, that means we are diluting the oil to the point where we're going to cause internal damage to the connecting rods to the crankshaft, all that good stuff. Okay, here's the diagnostic board. Notice that you have dip switches that are going to be set up. Notice that you have LEDs and the wiring. Basically, this is going to tell us what is going on with this compressor, electronically speaking. And by these indicating lights, you get a flash code, fault code. You can figure out what's going on internally. These compressors came out. Whereas we didn't have all these diagnostic tools. We had to, as service technicians, try to figure out what was going on. And that could be frustrating to say the least. Okay, I've worked on a lot of these. This is a Carrier 5D. Excellent compressors. They were originally designed for the US Navy back in World War II, and they're actually still used out in the field today. They made these with what they call an open drive assembly. So basically, you have you had to deal with parallel shaft alignment, angular misalignment. These motors had to be perfectly parallel to the shaft because this had a shaft seal. These compressors, I can't say enough good things about them. Carrier Corporation just made a super good compressor, and these things are still out there. Surprisingly, there's still a lot of these compressors out there. I've overhauled these things. I've rebuilt them. I've done alignments on them. The US Navy loves them, and I believe they're still being utilized today on ships as well as civilian applications. You will find these compressors still in widespread use on commercial systems. They do a very good job. Don't forget that these are a oil pressure pump type thing as far as your lubrication goes. They also have unloaders on here so you can unload the cylinders. We had a large version of this. I believe they went up to, I'm trying to remember, I think it was 5H120 or 5H160. I think it was the top end. That's basically where you had a 6-cylinder model. And basically, we would use those like for air conditioning plants on a ship. And they were unloaded. We would actually use unloaders in order to unload the suction valves as the pressure of the evaporator dropped. We would actually take and drop out cylinders so that we did not keep the compressor operating at full capacity. So the capacity control through unloaders, we could actually unload this thing down, if I remember correctly, down to about 35–40% of its rated horsepower tonnage. They work very, very well, very efficient, and probably not as good as some of the new technologies out there today. But these things were simple, they're easy to maintain, very easy to put together. Okay, here we have what appears to be a discus compressor designed here. Notice that we have our crankshaft, our force feed oil pump over here, our rings on the pistons, and of course you have a solenoid, which I believe is used for unloading purposes on this type of compressor. Okay, on this one here, we talked about this earlier, but this would be part of your scroll compressor unloading system utilizing the bypass ports. This is another picture showing the opening and closing of that solenoid in order for the refrigerant to open and close the bypass ports. In other words, we're going to change the capacity from 67% to 100% depending on the load requirements. Now here we have something interesting. Notice that the wiring that you see there off to the left indicates that this is a 3-phase power source. The reason why I know this is if you'll look at it, the motor sensors, they have one on 3 legs. Anytime you see this arrangement here, typically that means you're going to have a 3-phase power source. Now, this is typically like a Y connection. So notice that you're going to have these 3 windings are connected at the center. And then of course the resistance value here, resistance value here, and resistance value here must be the same. If they're not the same, That means you're going to have electrical issues with this unit, and you're going to have to take steps to figure out what happened, fix it, and get this thing back on the line. Now, this also has a sensor in order to determine what is going on with the voltage as well as the current draw. And this, by the way, can be found on page 557 under figure 23.34. And this item here is a three-phase Y. So you see the Y over here? This is a three-phase Y. Y wound motor with an internal thermistor protection to the solid state motor protection system. The motor sensors are thermistors, and this would be, I guess this is from Tecumseh Corporation. Okay, here, this appears to be part of that turbo core machinery. And basically, this is, remember, this is using the oilless design. This is found on page 573 under figure 23.61. This is the bearing control system and sensors for the turbo core oilless compressor. The tolerance on these things are exact. And by suspending this thing in a magnetic position, we are able to avoid the use of oil lubricants in order to keep this thing operating. Don't ask me all the particulars. Got these sensors, all these different things involved. I can't say that I've actually ever worked on one of these. I have seen them, but I haven't worked on them. Here we have the electromagnets of the radial bearing and of the axial bearing on the turbo core, which is found in the same page under item B. That would be 23.60. So we're utilizing magnets instead of lubricating oil. What a novel concept. When it works extremely well. If the magnetic field is lost, obviously this compressor is going to shut down very quickly. Okay, here we have a difference when this reciprocating compressor, notice that we have 21 psig here, okay, and we have 236 psig. Notice that the cylinder is all the way down. And so basically, what we're showing is the pressure drop across this compressor cycle. And I believe the idea here is just to show you what happens when you open up the discharge. So at this point here, we have 21 psig going in, 236 leaving. Okay, what does that indicate? Let's see what the book says. Okay, in this illustration right here, basically this is found on page 23.2. The pressure difference between the suction discharge of the compressor, and this is 404 alpha, which is a low temperature refrigerant, medium temperature system. The compressor only has to raise the pressure 180 psig for this thing to operate with this refrigerant. Okay, here in this particular case, difference of 180 psig. So the previous one, okay, let's just go to the next one. I'm sorry. Okay, here we have the Copeland semi-hermetic compressor. And once again, very simple to, this would probably be a single phase unit, could be a three-phase, oil cycle glass over here, suction gas comes in over here, and you will have a discharge service valve right here. You have various ports to hook up, like for high pressure, low pressure. Here's your valve plate assembly. These things are field serviceable. They're designed to give long life. The main thing you need to remember, proper refrigerant flow. We don't like leaks at all. We want the electrical characteristics to stay in their proper order in order for this compressor to operate. And when you take and ship a bad compressor back for rebuilding, you always want to transfer these blanks. When you pipe up your new one, you're just going to basically bolt up to the existing one. The blanks that are come from the rebuild or remanufacturing facility, you transfer these plates to the compressor. It goes back for rebuilding in order to get your core credit. Okay, the flexible shaft assembly for a direct drive system. This is going to be found on page 549 under figure 23.17. This is on a train compressor. Notice that we're going to use a dial indicator right here that is going to be clamped to the motor hub. And we're going to take and rotate this thing, and we're going to look for a differentiation of the needle here to tell us if this thing's in alignment or not. When we line these things up, and I'm just citing my naval experience, basically we were allowed less than 5 thousandths, and that was not a lot. And we've actually spent several days trying to align these things. They're terrible. They're a lot of work. Notice that you have your parallel misalignment, angular misalignment. It's pretty easy to see this. And over here, of course, this is your proper alignment. And in order to get there, must use a dial indicator with a magnetic base and follow the manufacturer's recommended alignment procedures. This would be on a direct drive motor to compressor. And don't forget, the compressor is going to have a compressor crankshaft seal on the end in order to prevent refrigerant from flowing outside of the compressor. A lot of work when you're doing this, trust me. Been there, done that. Okay, this shows the technician taking the crankshaft out of this semi-hermetic compressor. Here we have another, I believe this is a discus compressor. Of course, you have your compressor head here, your oil pump end over here, you got your discharge line over here, your suction refrigerant vapor, not liquid, is going to enter over here, which is going to go across the windings and, of course, cool the windings down, keep this thing cool. Oil level inside this compressor is going to be monitored right here. Another example of the Copeland semi-hermetic compressor, discharge valve, your compressor head. You have fins in order to get rid of some of the heat. You've got fins to get rid of some of the heat. Primarily what keeps these compressor semi-hermetics cool is the use of refrigerant vapor. Okay, in this particular application here, we have a scroll compressor with the unloading mechanism here that gives you the specs on how this thing is piped up, the dimensions. And on this scroll compressor, you find this illustration inside your textbook here. Okay, this is going to be figure 23.53 under page 569. The digital scroll compressor showing disengaging solenoid valve for bypass and discharge gas to the suction side of the compressor. So we have the ability to bypass, and you have a thermistor. You have a discharge connection here and your suction connection here. So basically you have a bypass factor for unloading this particular and disengaging solenoid valve for bypassing discharge gas. So if we don't need the full capacity of the system, this is one way that we take and put this thing into a bypass position so that the compressor is going to operate at a different rate pumping ratio. Okay, this is going to be found, these are your split commercial systems, and I believe this is found on page 576. Basically, we have a situation here. Let's see here. I believe there's also, this should be, excuse me, this is going to be on page 575 under figure 23.63. System operating with normal compression ratio. Notice that the condenser is large enough to keep the head pressure low. Okay. So in this case here, we have 171 psi-G. Here's your condenser. Your condensing temperature is 120, which is normal. 3.6 psi-G on the suction line here. So basically what is happening here is the refrigerant obviously is flowing from the flowing from this line right here, the discharge line of the condenser, and of course coming down here to your sight glass, metering device, evaporator coil, -20 degrees boiling temperature, and then of course the 5-degree room temperature. So this is a refrigeration application. Well, why we're worried about compression ratios? Because if the ratio is not correct, you could destroy the compressor. So the compression ratio, this is the math formula for it, absolute discharge pressure. In other words, you take the actual pressure at 15. Then you take the absolute suction pressure. Once again, you take the suction pressure at 15, and they're saying 14.7. For our terms of discussion, use 15, round it off. So you add these two numbers, divide, and then this will give you the ratio. And this will tell you, in this case, this is a 10.15 to 1 ratio. So that's how you figure out the compression ratio of a compressor, dividing the discharge pressure from the suction pressure and adding 15 to each number prior to doing the subtracting. And then of course, that's how you determine the ratio. Okay, in this particular situation right here, we have 9.7 inches of vacuum here. And this is with a normal compression ratio. Notice that the condenser is large enough, and we talked about that earlier. And the system also has, in this case, a dirty evaporator. So why is a dirty evaporator problem? Because we're not going to absorb all the heat. So what does that mean? Well, Larry, this is what it means. If this evaporator coil is dirty, if the fans are not operating at the correct speed, the chances of bringing refrigerant liquid back to the compressor are increasing at this point. Now notice that we're now in a vacuum at 9.93 psia or 9.7 inches of vacuum, and we still have the correct high pressure. And look at our compression ratio here. We got a problem here, guys. Take a look at that. 9.93 psia. Remember, this is the actual suction pressure plus the the 15 added. And in this case here, you take the discharge pressure 171.2 plus 15. Look at that ratio. It's too high. We got a problem there. So what we're saying is, if the system is dirty, if the condenser is dirty, you're going to have high compression ratios, and you will end up creating a lot of problems for the compressor. Okay, in this case here, I believe this is on page 576. Now we have a situation. Let's take a look at the compression ratio over here. 190 psig, 3.6 psig on the low side, air in at 95, air in at 95. Now look at the air coming out, 127 degrees. Now this is a foul, dirty condenser. Now we still have the right temperatures at 5 degrees in the evaporator of the store and -20 degrees. But look at our compression ratio here. 190 psig on the high side plus 14.7, we'll use 15. Then we'll take 3.6 plus 15 and we divide the two, and look what we got here, 11.8. So this compression ratio is a problem utilizing 134 alpha. And the reason why it's a problem, because we have a dirty condenser. What are we saying? You need to keep the condensers clean. That's an absolute. Last slide. We have 9.7 inches of vacuum, 190 psig, which is on the high side. This is 134A, got 127 degrees Fahrenheit, dirty condenser, 95 going in, 127 going out. Still at the -5 degree room temperature, trying to keep ice cream cold. We have a evaporator coil that's probably dirty. So basically, looking at this particular slide, we have a situation, we have 190 psig plus 14.7 or 15 divided by 9.93 psia. Look at the compression ratio. Once again, too high. Compression ratios can be done, and they should be done out in the field to evaluate if compressors are at their proper pumping capacity. And if you don't do this, the chance of the compressor scrambling, messing up, are increased. Thank you for your attention to this particular compressors.